also about the sort of deflection mechanics of it as well. It's going to be looking at the second half of today. Okay, so we talked again about that pipe. There are a handful of a few basic sort of loading types that we can apply to a structure, and they result in us having very simple formulae. I spoke a bit about it yesterday, but it's very good, even though these are relatively simple models. When I say a model, I mean like this formula here, that's a model. It's one way that we can represent the stress, right, using that particular model. The MI and I, it uses the continuum mechanics model. So there are relatively simple models. I teach a course back in Melbourne called Finite Element Analysis, which is sort of a more advanced structural course using computational methods to look at stress states. So we can look at any arbitrary shape and we can put any arbitrary loading on it and represent the stress state in the system. But still, I always come back to, with my students, recommending that they think about the stress loading in terms of these more simplified models. So things like all your continuum mechanics, so MY and I, force over area, your hoop stress, your longitudinal stress, and all these other ones. So even though these are simple models, as a practicing engineer, someone who consults a lot with industry, I still often go back to these sort of representations. And I've actually got a good example we'll maybe cover off. We'll cover off today of something that I'm currently consulting on, working on. We can talk about later. So yes, if we have a structure here, we have a structure, it's internally pressurized. It's a very common thing to have a pressure vessel. So you're holding a pressurized liquid. Actually, yes, this is another thing that we've been working on recently, is a new type of, not a new type, but a better type of a shock absorber. It's got multiple different sort of pressure vessels inside of it, and we used these exact formulas to sort of give us a rough estimation of how thick we should make the structure. Initially, when the people first did the design, they thought it should be, I think, 4.5 millimeters thick, and then when we put these numbers in, we were able to do a quick analysis and we could say, oh, we don't need it to be 4.5 millimeters thick, it can be like 1.5 millimeters thick, and we save a lot of weight and a lot of cost as well. So we internally pressurize it, and again, the key thing to remember is with all these systems, they need to be in static equilibrium, no matter which way you cut it. So if we cut it this way, that way, and we analyse the external loads that are being placed on the system, and when we cut it through a surface, the internal stresses, they have to balance each other out. So the sum of forces, the sum of moments always have to balance each other out. So here we've cut off a little section. When we cut it through, we have the pressure that's being applied to that area. So force is pressure over area, pressure times area. Right? So we have that pressure, we times it by the area, and then we have this stress over the little small area, which is just the little thickness times by the height. Then you can easily get that out to get this equation here, that's the hoop stress, right? This is known as hoop stress, or it's also known as circumferential stress, or it's also known as tangential stress. That direction, that sort of direction around the hoop, it's either known as hoop, tangential, or circumferential directions. So you can listen to them. And even though we have that same internal pressure still being applied, if we cut it a different way, again, you can see that we're going to have that pressure, it's going to be acting on the end cap. It's pushing on that end cap, that same pressure has to be resistant, the system has to be in static equilibrium, so the internal stresses subsequently, you can calculate, you have that thickness, the area, the radius, right? So you end up with this equation here. We can see that these two are different by this factor of 2. So that obviously means that this hoop stress is always going to be twice that of the longitudinal stress. Now, even though I have this hoop stress here, stress 1, and stress 2 at the same location, I can't add them together. It's not like I can have stress, the hoop stress, and longitudinal stress, or also known as the axial stress. I can't simply just add them together. Because as we talked about yesterday, forces, or stresses, like forces, they are vectors. They have both velocity and magnitude and direction, right? So just like, if I move 1 meter forwards and then 1 meter to the left, I haven't moved net 2 meters. I can't add that 1 meter to that 1 meter because that is a vector, right? So these two vectors, the hoop stress and the axial stress, or the longitudinal stress, you can't just add those two things together because they're acting in different directions. They will relate to each other in terms of how they stress the material, and you'll talk about that in a future course. But that you can't just simply say, okay, my overall stress is going to be stress 1 plus stress 2. That doesn't work. You can do a similar thing with a spherical vessel if you just have a sphere. Other stresses that we've got, we have obviously force over area. We all know that, that's a nice axial stress. We have shear stress, we talked about that yesterday. We have bending moment, internal bending moments lead to this. If you have like a curved section, it's this, but I'm not going to worry about that. We also have torsional stress. Sorry, should I say that here? Think back to that example of pipe. Actually, I'm going to draw this. Be aware, my drawings are really good. Okay, so go back to that example. We have a pipe, right? So we have it's a perfect pipe. It's got an internal pressure P, right? That internal pressure P is going to be generating. If I say that I have X, Y, and obviously we know that X, Y, Z is coming out of the page. Yeah. So Z is coming towards us. We know that this is going to be generating a stress in the X direction, hoop stress, the axial stress. It's also going to be generating a hoop stress, which is sort of at this point here, it's going to be going in the Z direction. So if you think about just the stress at that point there, it's going to have an axial stress due to the stress in the X direction due to the axial or longitudinal stress. That's PR on 2T. It's going to have a stress on the Z because that's going to be the sort of hoop direction at that point. So it's going to have a stress in the Z, that's the hoop stress. You could also apply a force. There might be someone's while simultaneously like pressurizing the system. For some reason we have like some force in the X direction. So that force in the X direction is also going to add another force in the X. So I'm actually write this down. So this is E on 2T. This is E on T. Stress. That's the force on area. In addition to that, we might have some sort of, there might be some distributed load acting on it. That distributed load is going to, and it might be mounted here and here, that distributed load is at that point, this point of interest, it's going to be inducing a shear stress and the bending moment. So we would have the bending moment, which which direction is that going to be adding a stress in? Is it the X, Y, or Z? If we have this distributed loading on top here, it's going to induce a bending moment at that point. Which direction? So remember when we bend this down, this side, like it's gonna, that side's going to go into compression, that side's going to go into tension, and so it's compressing. It's getting shorter in the length of the X direction, and so the stress is in the X direction. So we're going to have another stress in the X, which is going to be due to bending. And that is negative my on I. We are going to have a shear stress due to the internal shear moment, internal shear force, V. That's going to be VQ on IT, which you talked about. And that stress, that shear stress we talked about yesterday, it's on the X face in the Y direction. So it's vertically going up and down, but it's on the face which is perpendicular to the X direction. So if we write that as XY, that is also, I'll talk about that bit later, but that's also going to be numerically, it's going to have the same value as that on the stress in the X direction on the Y face. But that's not all that this pour pipe's undergoing. For some reason, also someone's applying a torque to it. Right? So someone's come along, and you can either write a torque as a circle, or I don't know if you've seen this, but you can also do it if you do an arrow with two heads on it. That also means that someone's applying a torque that way. So that means someone would be applying a torque this way about it. So a torque T, that's also going to induce another stress. Pardon?
How to show
How to, sorry?
How to represent
for a torque, yeah, there's two arrows. An arrow.
That's 2 arrows.
Yeah. So that means it's a torque about that direction. So it's a torque about the x-axis. Otherwise you have to draw like a hoop around the x-axis, and because I can't draw all through the page, I can't do that. We also have a torque being applied. And that's going to induce another, that's the torque stress. And that would be the torque times by this radius divided by J, where J is the polar moment of the area. So where we did with the second moment of area, it was the integral of y dA, so it was the integral of the distance away from the centroid over the whole area, of the distance squared, so it was y squared dA. This J is, it's still the area integral, but it's the radius squared, so it's distance from the center to any point radius. But you don't need to remember, just look at the formulas in the tables. But it's good to know where it comes from. So that's that. And that, for that particular point, that would be XZ. For this point up here, it's on the X face, but it's in the Z direction. So you look at all this, like look at all this pour pipe. It's undergoing so much. What does this pipe have to do to anyone else? But you can see like all the different stresses, and they're all acting in different directions. And the question would be, okay, how do we combine these? We know that we can't simply just add this one and this one, but can we just add these stresses all in the x-axis? Can we add them together? How do these stresses interact with the shear stresses? Sure, these ones are stress in the x direction, but is that any different to the stress in the x direction on the y face? Like, what's the difference between all of these? And that's what we're going to sort of go through in the first section. One of the fundamental principles of stress analysis of continual mechanics, which is what we're dealing with. When I say continual mechanics, that just means we can divide the structure into smaller and smaller and smaller parts forever until we get to like infinitesimals. So we can keep making it smaller and smaller. It doesn't have like discrete sections. So one of the key things about stress analysis and continual mechanics, and particularly for like linear analyses, is this principle of superposition. What that means is if I have a vector in a particular direction and another vector at that same point in the same direction, you can just add them together. So at that point on our pipe, if we have a stress in the x direction and another stress in the x direction, I can just add them together. But what I can't do is I can't add, like I can add a sigma x plus sigma x, but I can't add sigma x plus tau xy. Even though they're the same stresses in the same directions, they are different. So this allows us to add all those sigma x's together, all the sigma y's, all the sigma z's, all the tau xy's, all the tau xz's, all the tau yz's. Those individual components you can add together, but you can't combine them with different vectors together. So that's really, really important. So that simplifies our problem here a great deal. So, yeah, let's quickly do this problem. Yeah, let's do this. Okay, we can do this one. So let's do this problem here. We have a set of pliers, really easy. We're just compressing them here. They pivot about this point here. They have a distance from that point to where you're applying your hands of 250 mil. We're applying a 10 kilogram or 10 Newton load to it. And then we've put a piece of very hard tubing of some sort, a distance of 50 millimeters away from that pivot point. And I want to analyze the stresses on that plane. So halfway from the pivot point to that, there's steel, whatever it is, halfway through that, so 25 millimeters away. I want to analyze the stresses at A and B. So do that. One key thing here is even though it looks a bit different because it's a, we have different angles going on here, but we still have a force multiplied distance, and that force and the distance are sort of at 90 degrees of each other. And so is, like we have a distance here, and the force that's going to be acting on this surface is going to be 90 degrees to that distance. So it's still just, you can sort of treat it like being a straight line. That 45 degrees, yeah, you don't need that rule. Okay, have a go at that. So we're back, and we can finish off that problem.
对。